In this video, we want to learn about improper double integrals. Look at this first example. Integral from 1 to infinity, integral from e to the negative x to 1 of the function 1 over x to the 3y dy dx. As you can see, this is improper integral because we have infinity for this upper limit. But as you know, first we have to evaluate this inner integral. We have to find the integral of 1 over x to the 3y with respect to y from e to the negative x to 1. Then we have to find the outer integral, which is with respect to x. So let's focus on the inside. We want to find the integral of the function. We want to find integral of the function 1 over x to the 3 y dy. For finding this integral, if you pay attention, 1 over x to the 3y can be written as 1 over x to the 3 times 1 over y dy. 1 over x to the 3 times 1 over y is 1 over x to the 3y. The reason that it's a good idea to write this function in this form is that now finding the integral of this function is very easy. If you pay attention, integral of 1 over y with respect to y is ln of y. Attention, this is a coefficient for this function. So this integral equals 1 over x to the 3 because it's a coefficient. When we take integral with respect to y, everything other than y is a number. So this is a number. We write the number and then we integrate this. Integral of 1 over y dy is ln of y, or ln of absolute of y. Now that we know the answer of the inner integral, let's calculate this. Integral 1 to infinity. Integral of 1 over x to the 3y is 1 over x to the 3 ln of y. 1 over x to the 3 ln of y from e to the negative x to 1 dx. Now we have to substitute 1 and e to the negative x for y, and we have to find the value of this expression. This equals integral from 1 to infinity 1 over x to the 3 ln of 1 minus 1 over x to the 3 ln of e to the negative x. The reason that you don't need to put absolute for this is because e to the negative x or e to the x is always positive. So it's not really necessary to put absolute for this expression. dx. Now let's simplify this expression inside the bracket. ln of 1 is 0, so this expression is 0. ln of e to the negative x, ln of e to the negative x is basically negative x ln of e. We know that we can bring the power down to here because this is one of the properties of logarithmic functions. By moving this and bringing it down to here, we have negative x ln of e. But ln of e is 1, so this equals negative x. In general, it's good to know that ln of e to the power of any function equals that function. And so ln of e to the negative x is negative x. So this part is 0. And because this is negative x times negative 1 over x to the 3 is 1 over x to the 2. So we have integral from 1 to infinity 1 over x to the 2 dx. This negative with this negative cancels. X over x to the 3 is 1 over x to the 2. Now for finding this improper integral, first we have to integrate this and then we have to substitute infinity and 1 for x to find the value of the integral. But attention, because infinity is not a number, When we substitute infinity for x, when we integrate this is not mathematically right. The better way is to write this integral in the limit form, then calculate the integral. But for now, let me show you the easier way for finding this integral. Then I show you the better way for calculating this integral, this improper integral, which is more mathematical way. But for now, we follow the easy way. Integral of 1 over x to the 2 is basically integral of x to the negative 2. We can write 1 over x to the 2 in the form of x to the negative 2. And based on the power rule, this integral equals x to the negative 1 over negative 1. We add 1 to the power and we put that power in the denominator based on the power rule for integrals. But x to the negative 1 over negative 1 is basically, this expression is basically negative 1 over x, because we can bring this x to the negative 1 to the denominator and we can put this negative in the numerator. So the answer of this integral is negative 1 over x. Negative 1 over x from 1 to infinity. Now we have to substitute infinity for x, 1 for x, and we have to subtract. When we plug in infinity here, again, it's not mathematically right to say we plug in infinity here, because infinity is not a number, so you cannot substitute infinity basically here. But because we want to write our solution in the easier way and we don't want to involve in limit, for that reason we suppose we substitute infinity here. If we plug in infinity, any number over infinity is 0. So this equals 0 minus, now we plug in 1 for x. Negative 1 over 1 is negative 1 minus 1. And all of this equals 1. So the answer of this improper double integral here is 1. Now let me show you the better way for writing and calculating this improper integral. If you want to calculate improper integral in the form of integral 1 to infinity of 1 over x to the 2 dx, it's better to write it in the form of limit integral from 1 to a variable. You can name any variable you want. I choose t, and t goes to infinity because this goes to infinity, so t goes to infinity. So this upper limit is infinity, is approaching infinity. This is the proper way for writing this improper integral, and the function is 1 over x to the 2 dx. 1 over x to the 2 dx. Integral of 1 over x to the 2 is negative 1 over x. This integral is 1 over negative 1 over x. First we have to write limit t approaches infinity, 1 over x from 1 to t. Now for finding this limit, we substitute t here, and then we substitute the 1, and t approaches infinity. So this equals limit t approaches infinity, 1 over t, we substitute t, and then we substitute 1. I forgot to put negative here, negative, minus, now we plug in 1, negative 1 over 1, we have this. Now, because t approaches infinity, the limit of negative 1 over t is similar to here is 0. So this equals 0, because this part is 0, and this is 1. So 0 plus 1 equals 1. As you can see, the answer is the same, but when you calculate this improper integral in this form, the way that you write your solution is not mathematically right. If you want to follow the best way for calculating improper integrals, this is the better way instead of this. But it's up to you to choose between these two methods. Let me show you another example of improper double integrals. Here we have integral from -1 to 1, integral from -1 over radical 1 minus x to the 2 to 1 over radical 1 minus x to the 2 of the function 4y plus 1 dy dx. Why this integral, why this double integral is improper? Maybe you wonder, I can't see anything that shows that this is improper. We don't have any infinity, but if you pay attention, this is improper integral because this upper limit and this lower limit involve are what? These are 1 over radical 1 minus x to the 2, and the other one is -1 over radical 1 minus x to the 2. But look at this. X is changing from -1 to 1. When x is changing from -1 to 1, please attention. This is the reason that this is improper. When x is changing from -1 to 1, if you consider 1 for x, the denominator is approaching 0. 1 minus 1 is 0. And we have a number over 0, similar to that here. 1 over something that approaches 0. And these are infinity. So the upper limit and the lower limit of this double integral, they approach to infinity when x gets close to -1 and 1. For this reason, this is an example of improper integral. First, for finding this improper integral, we have to calculate this inner integral. Integral of the function 4y plus 1 with respect to y. So this integral equals integral from -1 to 1. Integral of 4y based on the power rule simply is 2y to the 2. And the integral of 1 is y. Attention, we integrate with respect to y, so integral of 1 dy is y. And attention, derivative of 2y to the 2 is 4y. So this is the answer of the integral. Now we have to substitute the upper and lower limit of the integral. -1 over radical 1 minus x to the 2 and 1 over radical 1 minus x to the 2 dx. If we substitute 1 over radical 1 minus x to the 2 for y here, because this raises to the power of 2, so the radical cancels, and only we have 1 over 1 minus x to the 2, so we have 2 times by 1 over 1 minus x to the 2 plus y. For y we substitute the expression 1 over radical, so we have 1 over radical 1 minus x to the 2. All of this minus, now we substitute this for y here, so we have 2 times y. If you raise this to the 2 again, you have 1 over 1 minus x to the 2 plus y is -1 over radical 1 minus x to the 2 dx. And of course, we have to put a bracket for all of this. Now, please attention. Here we have 2 over 1 minus x to the 2. Here also we have 2 over 1 minus x to the 2, but here we have between them a negative, so they cancel each other. 1 over radical minus times minus is plus, plus 1 over radical in total is 2 over radical, so this equals, so we have integral -1 to 1 2 over radical 1 minus x to the 2 dx. If you pay attention, this is improper integral because when x approaches to 1 or -1, this denominator gets close to 0, so this expression goes to infinity. So this is improper integral. I am going to show you how we can find this integral in the easy way, not the limit form, but definitely it's better to first write this integral in the limit form and calculate this improper integral with the limit form. But usually students prefer to find these improper integrals just with the easier method, which is of course not the limit form. Integral of, if you remember from integral formulas, integral of 1 over radical 1 minus x to the 2 dx is sine inverse of x, or arc sine of x. So this is a formula that we know from integral formulas. So this integral equals 2 sine inverse of x from -1 to 1. Now simply we have to plug in 1, so we have 2 sine inverse of 1 minus 2 sine inverse of -1. The angle that its sine is 1 is pi over 2. So sine inverse of 1 is pi over 2. The angle that its sine is -1 is negative pi over 2. And this equals, this is pi plus pi, the answer is 2 pi. And about sine inverse of -1, maybe you are thinking this angle that its sine is -1 is also 3 pi over 2. Why I'm not using 3 pi over 2 for this? Because remember, sine inverse of x is always limited between -pi over 2 and pi over 2. And so the answer that you choose for sine inverse should always be in this interval, be between -pi over 2 and pi over 2. So you cannot choose 3 pi over 2 for that number. So the answer of this double integral, improper double integral, is 2 pi. Now look at this example. Integral from -infinity to infinity. Integral from -infinity to infinity of the function 1 over x to the 2 y to the 2 plus x2 plus y2 plus 1 dx dy. This is completely clear that we have improper integral here, because we have infinity in the lower limit and upper limit of the integral. For finding this integral, first we have to integrate this with respect to x. Then we have to integrate the answer of that with respect to y from -infinity to infinity. But for finding this integral, the easier way for finding this integral is to write this in the form of -infinity to infinity. -infinity to infinity. If you attention, the expression in the denominator can be factored in the form of x2 plus 1 times y2 plus 1 dx dy. If you multiply this bracket by this bracket, simply you can see that it gives you exactly this expression. So for finding this double integral, first we factor the denominator and we write it in the form of 1 over x to the 2 plus 1 times by y to the 2 plus 1. Now, because this region is a rectangle, x is changing from -infinity to infinity and y is changing from -infinity to infinity. Because we have a rectangular region, and because this function here can be written in the form of 1 over x to the 2 plus 1 times by 1 over y to the 2 plus 1. So because this function can be written as product of two parts, that one part is only in terms of x and the other part is only in terms of y, for these reasons, instead of finding this improper double integral in this form, we can write this double integral as product of two single integrals in the form of -infinity to infinity of 1 over y to the 2 plus 1 dy times by integral from -infinity to infinity of 1 over x to the 2 plus 1 dx. The reason that we can do this is again because this function is product of these two functions, and also because these limits of the integral is a rectangular region, and for this we can do this here. Now simply we have to find the value of this single integral, which of course both of them are improper. But now we have to work only with single integrals, not double integral. Based on integral formulas, integral of 1 over y to the 2 plus 1 is tangent inverse of y from negative infinity to infinity. And the other integral is tangent inverse of x from negative infinity to infinity. Again, I have to mention, this is not the proper way for finding improper integrals. It's better to write these in limit form, but because it makes calculation more complicated and it makes the video longer than usual, I prefer to just follow the shorter method for writing these improper integrals. Now, simply, we have to substitute infinity for y and negative infinity for y, and we have to subtract. Tangent inverse, if we substitute infinity, tangent inverse of y when y approaches to infinity is pi over 2. So this equals pi over 2 minus, when y approaches to negative infinity, tangent inverse of negative infinity is negative pi over 2. For the second expression that here we have same thing. When x approaches infinity, we have pi over 2. When x approaches negative infinity, negative pi over 2. The first bracket is pi, the other bracket is also pi, so the answer is pi to the power of 2. Please attention, instead of saying we substitute infinity for x, it's better to say x approaches infinity. And when x approaches infinity, this expression approaches, for example, pi over 2. And in this way, we are saying that this is a limit. But definitely the best way is to write it in the limit form and then do this calculation. But the answer at the end would be the same. So the answer of this improper double integral is pi to the power of 2. Now look at this example. Integral from 0 to infinity, integral from 0 to x of x e to the power of negative x to the 2 over y dy dx. Again, this is improper integral because we have infinity here. So this is improper integral. But here we have to first calculate the inner integral, which is the function is x e to the negative x to the 2 over y with respect to y. But the problem here that we have is that finding the integral of this function with respect to y is impossible. We cannot find this integral in terms of elementary functions. So finding this integral with this order is impossible. So we have to think to changing the order of integration here. So we have to change the order. We have to reverse the order of integration. So we want to try to write this integral in the reverse order, which is finding the integral in the form of x e to the negative x to the 2 over y dx dy. Because we want to change the order of integration, first we have to draw this region, then we have to find the proper upper limit and lower limit for the new double integral. Let's draw the region here. Attention, x is changing from 0 to infinity. Y is between 0 to x. So y is between 0 to x. When y is changing between 0 to x, what is y equals 0? Y equals 0 is basically the x-axis. Y equals x is this line here, which of course continues this way. Y is between 0 and x, so y is going from 0 to x. This is the region that we have. And we don't have any limit for this side because x, if you pay attention, is going from 0, x is going from 0 to infinity. So this, like a triangle, extends to the right forever. We don't have anything to limit that. So this goes forever to the right. We can continue this forever to the right. Now look at this triangle and try to find the lower limits and upper limits for x and y. Of course, we have to start with x. For finding from this triangle, for finding the lower limit and upper limit for x, as you know, we have to draw vectors parallel to x-axis. Here, if you pay attention, I draw vectors parallel to y. Now for x, because we want to find the lower limit and the upper limit for x, we have to draw vectors parallel to x. If we draw a vector this way, and if we extend this vector, we can see that this vector, this line, whatever you want to name it, it enters the region at here. If we draw another one, the vector enters the region when it intersects this line. So this is the lower limit, and of course it can go forever to the right. So this goes forever to the right. So based on this, what is the lower limit and upper limit for x? As you can see, the lower limit of x depends to this line. For x, we enter the region at this line. But what is this line? This line is x equal y or y equals x. This line here is y equal x. Because we want to write the lower limit and upper limit of x here, so the lower limit of x is y. You have to write the function in terms of y here. So it's not right to say the lower limit is x. Here you want to say x is between, it should be in terms of y, the other variable. So x, the lower limit for x is y. What about the other upper limit for x? As you can see, x can go forever to the right. So the upper limit is infinity for x. What about y? For y, we have 0 to infinity, because it starts from here, this rectangle, if you pay attention, y starts from this line, which is 0, and it can go up forever. So y is changing between 0 to infinity. Don't make this mistake to think that, okay, the y also starts from 0 and it ends at this line. No. For the outer integral, always you have to write numbers or infinity for the outer integral. But for the inner integral, we can have functions. X is from y, which is this line. X equals y is this line. So x is changing from y to infinity. But for the outer integral, please attention, when we want to integrate with respect to y, it should be numbers only here. Y is from 0 and it goes up, because if you extend this, this goes up forever to infinity. So y is changing from 0 to infinity. Now that we have reversed the integral, the order of integration, now if you pay attention, we can find the integral of this function with respect to x. The reason is that if we suppose this as u, its derivative is almost here. du is almost here, not exactly, but almost. And so we can integrate with respect to x from this function. The integral of this function equals integral from 0 to infinity. Integral of this function with a simple u substitution, which I will show you after I finish my calculation here. For now, suppose we know this integral. If we use a u substitution to find this integral, the answer of this integral is negative y over 2. The answer of this is negative y over 2 e to the power of negative x2 over y. All of this from y to infinity dy. Now, as you know, we have to substitute infinity for x, y for x, and then we have to simplify. This equals integral. This equals integral 0 to infinity. When we substitute infinity, please attention, when we substitute infinity, it's better to say when x approaches infinity. X goes to infinity, so x to the 2 also goes to infinity. So this power is going to negative infinity. We know that in exponential function, this is exponential function, when the power approaches negative infinity, the exponential function approaches 0. Let me explain this in detail again. x is approaching infinity. So this exponent is approaching negative infinity. And in exponential functions, if you remember, when we go far to the left toward negative infinity, as you can see, this exponential function is approaching 0. So when we substitute the upper limit, this would be 0. So we have 0 minus, we have 0 minus, now we have to substitute y here. Y to the 2 over y is y, so we have minus negative y over 2e to the power of negative y dy. And if you pay attention, negative times negative is positive, so we have integral. So we have integral of 0 to infinity of y over 2e to the power of negative y dy. For finding this improper integral, if we use integration by parts method, simply we can see that this integral equals negative 1/2 e to the power of negative y times y plus 1 from 0 to infinity. I will show you after I finish my calculation here how we can find this integral with the integration by parts method. Now we have to substitute infinity for y, and we have to substitute 0 for y, and we have to subtract them from each other. When we substitute infinity for y, here we have e to the power of negative infinity. Y approaches infinity, so the exponent approaches negative infinity, and e to the negative infinity, exponential function when the power x approaches infinity, negative infinity, is 0. But the thing that is important here is to notice that you substitute infinity also here, and this is also infinity. This is 0, this is infinity. 0 times infinity is not necessarily 0. So this is indeterminate form, and you have to use something like L'Hopital to find this. But for now, let me tell you, when we substitute the infinity, this is 0, this is infinity, 0 times infinity, in this case is 0. So when y approaches infinity, this expression approaches 0. So we have 0. But I will show you the reason that why it is 0, why it's not other number with the L'Hopital. But for now, it's 0. What about 0? If we substitute 0 for y, this is e to the 0, 1, this is 1, so minus 1/2, so 0 minus 1/2, and this equals 1/2. So the answer of this really challenging, complicated, improper double integral is 1/2. And attention, remember the interpretation for double integrals, it's volume. We know that when we calculate integral of a function, of a two-variable function on a region, we are finding the volume under that surface over that region. So the volume under this surface over this rectangular infinite region, the volume under the surface is just 1/2. Now, let me explain to you the things that we left and we didn't do them properly. I didn't show you the details. For example, I told you I will show you why this integral is this, why this integral with integration by parts is this, and the other thing is why when we substitute infinity in this expression it is 0. 3 things I have to show you to complete my solution. So we want to show that integral of x e to the negative x to the 2 over y dx equals negative y over 2e to the negative x to the 2 over y. For this we use the u substitution method. We suppose this exponent as u, negative x2 over y as u. Then from this du, derivative of u is negative 2x over y dx. Attention, we want to take the derivative of this with respect to x. And so this is a number. So we don't need to use quotient rule to find the derivative of this fraction. Y is a number here. So we write the number, the derivative of the numerator is negative 2x. And if you use quotient rule to find the derivative of this fraction, the answer of course would be the same. If we solve this relation for dx equals y times du over negative 2x. Y du over negative 2x. Now we can do the substitution. So this integral equals integral of x e to the power of, the exponent is u, so e to the u, and dx is y du over negative 2x. If we cancel x from numerator with x from denominator, we have negative 2 in the denominator, which we can move this negative 2 to the outside, and we can write it simply as a negative 1/2. Because negative 2 is in the denominator, basically it's like a negative 1/2 integral of e to the u. The other thing that we can move outside, if you pay attention, y here is also a constant. So we can move it to the outside of the integral. So we have negative y over 2 here. And then we have e to the u du. Attention, the variable in this integral is u. And so y is like a constant. So we can move it to the outside. Integral of e to the u is e to the u. So this integral equals negative y over 2. Integral of e to the u is e to the u, but u is this. So the answer of this integral is e to the negative x to the 2 over y. And don't forget to add a c to the answer for this indefinite integral. So the integral of x e to the negative x to the 2 over y is negative y over 2 e to the negative x to the 2 over y, which is exactly this answer that I used here. The other thing that I have to show you is that the integral of y over 2 e to the negative y is negative 1/2 e to the negative y times by y plus 1. For this we use integration by parts method. So we want to show that the integral of y over 2 e to the negative y dy equals that expression. Yes. For this, attention that this 1/2 that here we have y over 2, this 2 in the denominator is like a 1/2, and we can move it to the outside of the integral and we can write it this way. So we can put the 1/2 outside like this. For finding this integral, simply if we suppose u as y and dv e to the negative y dy, then from these two relations, from this du is dy, and from this if we integrate, v equals integral of this is negative e to the negative y. Let me remind you the integration by parts formula. U dv, integral of u dv is uv minus integral of v du. Based on this formula, the answer of this integral equals, don't forget you have a 1/2 times by u times v. U is y, v is this, u times v is negative y e to the negative y minus integral of v, which is negative e to the negative y, du, which is dy, as you can see here. Du is dy. This equals 1/2 times by negative y e to the power of negative y. Negative times negative is positive. Integral of e to the negative y is again negative e to the negative y. So the answer is negative e to the negative y plus c. Let me erase here so I can simplify my answer. Now if you pay attention, we can write this answer by factoring a negative y from a negative, basically only a negative from these two terms. If we factor a negative, this answer can be written in the form of. The other thing that we can factor is e to the negative y. So if we factor a negative and e to the negative y from these two terms, we can write this answer in the form of negative e to the negative y over 2 times y plus 1 plus c. This answer is exactly the answer that we used here. The integral of this expression is negative 1/2 e to the negative y times y plus 1. And this is exactly same answer. The other thing that I have to show you is this part. Y, the limit of this expression when y approaches infinity is 0. So I want to show you that. I want to show you limit of negative 1/2 e to the negative y times by y plus 1 when y goes to infinity is 0. Attention that simply we can write this expression in the form of limit y goes to infinity. Because we want to use L'Hopital rule for finding this limit, I want to move this part to the denominator. E to the negative y goes to the denominator and we can write it as e to the y. And y plus 1 is in the numerator. This negative 1/2 is just a coefficient which you can put it outside of the limit here, or simply you can put the negative 2 or negative 1/2 here as a coefficient. So 2 e to the y in denominator and numerator is negative y minus 1. If you multiply negative 1 in the numerator, we have this. Now we use L'Hopital rule. From L'Hopital rule, we know that we have to take derivative of the top and derivative of the bottom. Derivative of numerator, derivative of negative y is negative 1. Derivative of the denominator is 2e to the y. Now y goes to infinity, numerator is a number, denominator is exponential function, and y goes to infinity. So the denominator approaches infinity. Numerator is a number over infinity is 0. So this limit is 0 as we expected. Let me tell you why, just by saying this is 0, why we cannot conclude this limit is 0. Because when y goes to infinity, this part approaches 0. But this bracket goes to infinity because y goes to infinity. 0 times infinity is not necessarily always 0. You have to find its limit because it is indeterminate form. And this completes the solution of this really challenging question. Let me show you another improper double integral. Integral 0 to 1, integral 0 to 3 of x to the 2 over y minus 1 to the power of 2/3 dy dx. Because this function has two parts. One part is only in terms of x, the other part is only in terms of y. And the region of the integral is rectangular. We can separate x and y and we can write this integral, this double integral, in the form of product of two single integrals. So we can write this in the form of integral 0 to 1 of x to the 2 dx times by integral 0 to 3 dy over y minus 1 to the power of 2/3. Attention, if you multiply this by this, then we have the original function. For finding this integral, we can bring the expression in the denominator to the numerator and we can write it as y minus 1 to the power of negative 2/3 dy. Now we have to find this integral, the value of this integral, and then we have to multiply them by each other. This integral is a simple integral and it is not improper integral. But this integral is improper integral because this expression was originally in the denominator and it was 1 over y minus 1 to the power of 2/3. From 0 to 3, we have a number that makes the denominator 0 and then this fraction goes to infinity. What is that number? That number is 1. When y is 1, if y approaches 1, 1 minus 1 is 0. And so the denominator approaches 0 and then this fraction goes to infinity. So this is improper integral and it is improper at 1. Because of that, we cannot directly find this integral without splitting this integral to 2 integral. So for finding this integral, if you want to do it in the right way, you have to split this integral at 1, because 1 is the point that makes this integral improper. So for the first integral, easily we can use the power rule. Integral of x to the 2 is x to the 3 over 3 from 0 to 1. But for the next integral, we have to write it integral 0 to 1 of y minus 1 to the power of negative 2/3 dy plus integral 1 to 3 y minus 1 to the power of negative 2/3 dy. The value of this expression is 1 over 3, because if we plug in 1, this is 1 over 3. If we plug in 0, this is 0. So this is only 1/3. We have to multiply 1/3 in the bracket. For this integral, again, if you want to write it in the right way, you have to write it in the limit form at 1. But let's follow the easy way. So I'm not going to write this in the limit form. If you want to do it, you have to write it limit integral 0 to t approaches 1 of y minus 1 to the power of negative 2/3 dy. But it's not really important to write it this way. Of course, that would be the better way, but I am going to follow the easy way. So I'm going to just find the integral with the power rule. Based on the power rule, integral of y minus 1 to the power of negative 2/3 is y minus 1 to the power of 1/3 all over 1/3 from 0 to 1. And of course, the other integral is also the same, y minus 1 to the power of 1/3 all over 1/3 from 1 to 3. So we have a 1/3 here. If we plug in 1 here, this is 0, 1 minus 1 is 0. If we plug in 0 here, 0 minus 1 is negative 1. Negative 1 to the power of 1/3 is again negative 1. So we have negative 1 over 1/3. But attention, we subtract this from this, so it would be plus 1 over 1/3. So let me write it step by step. When we plug in 1 in this expression, this would be 0 minus. When we plug in 0 in this expression, we have negative 1 to the power of 1/3, which is negative 1 over 1 over 3. Negative 1 over 1/3 is negative 3. So we have negative 3 plus, now we plug in 3 and 1. If we plug in 3 here, 3 minus 1 is 2, 2 to the power of 1/3. So we have cube root of 2 all over 1/3, which would give you a 3 in numerator. So we have 3 cube root of 2. This 1/3 is divided by 1/3. So it's like multiplying by 3. So 3 goes to numerator. And if you plug in 1, if we substitute 1 for y, this is 0. So minus 0. This bracket is 3. So we have 3 plus 3 cube root of 2 times by 1/3. So we have 1 over 3 times by 3 plus 3 cube root of 2. If we factor a 3 from this bracket, that 3 with this 1/3 cancels. So the final answer is 1 plus cube root of 2. I hope by watching this video you have learned about improper double integrals. If you like this video, please subscribe in my channel and see you in the next videos.